In this session, we will talk about SVM, Support Vector Machines. Is a machine learning algorithm that are used for classification and regression purposes. SVMs are one of the powerful machine learning algorithms for classification, regression, and outlier detection purpose. The original SVM algorithm was developed by Vladimir Vapnik and Alexei Ya in 1963. Then, the current standard was proposed by Corina Cortez and Vapkin in 1993 and published in 1995. SVM can be used for linear classification purposes. In addition to performing linear classification, SVM can efficiently perform a nonlinear classification using the kernel trick. Kernel trick enables us to implicitly map the inputs into high-dimensional feature space. How does SVM work? The basic principle behind the working of support vector machine is simple: create a hyperplane that separates the dataset into classes. Let us start with a sample problem. Suppose that for a given dataset, you have to classify the red and blue sample. Your goal is to create a line that classifies the data into two classes, creating a distinction between red triangle and blue triangle, as you can see in this picture. In the above visualization, which one do you think would better differentiate the data into two classes, as I mentioned to you, with red line and or green line? To this aim, there can be many lines that can do this job. Therefore, there is not a single line that you can agree on which can perform this task. In the blue figure, we have a green line and red line. You can see here the green line and red line. Which one do you think would better differentiate the data into two classes? The question that I'm asking you properly. However, we still have not concentrated the fact that it is universal line that would classify our data most efficiently. For example, the green line cannot be ideal line as it lies too close to the blue classes. As I mentioned to you, the green line cannot be the ideal line as it lies too close to the blue class. Therefore, it doesn't provide a proper generalization, which is our end goal. Let's talk about support vector machine intuition. We should be familiar with some SVM terminology. For example, we have to learn about what is hyperplane, what is support vector, what is margin. Hyperplane is a decision boundary which separates between given set of data points having different class label. The SVM classifier separates data points using a hyperplane with a maximum amount of margin. Support vectors. Support vectors are the sample data points which are closest to the hyperplane. These data points will define the separating line or hyperplane better by calculating margins. What is margin? A margin is a separation gap between the two lines on the closest data points. It is calculated as the perpendicular distance from the line to the support vectors or closest data points. In SVM, we try to maximize this separation gap so that we get maximum margin. The following diagram, as you can see, illustrate this concept visualization. This is the hyperplane, this is support vectors, and this is the margin. What is our target? A margin is a separation gap between the two lines on the closest data points. And the blue color, the blue sample, and the blue and the red samples are support vectors. The yellow line is a hyperplane. Let's have a look in this picture with details. We call functionality of SVM. The image represents how an ideal SVM classifier looks when we visualize it on a 2D plane. There are two classes, negative and positive. As you can see here, negative is red color, positive is blue color. The hyperplane separates the data and helps in classifying the new input data points based on its value. Yes, exactly. The hyperplane separates these two classes. When the hyperplane for the decision boundary is generated, these nearest points through which the two margin plane pass are called support vector. The optimal decision boundary is the one that has the maximum distance between two margin hyperplanes. The distance between them is known as a margin. Hence, the SVM algorithm works on maximizing the margin. Let's have a look on linearly or non-linearly separates. When data points cannot be separated with a straight line or a straight hyperplane, those types are known as a non-linearly separated. In such a situation, SVM kernel acts upon and convert low dimension into a high dimension so that the data points are linearly separated. For example, in this image, use a mapping function. You see the mapping function here? They use the mapping function to transform a two-dimensional input space into the three-dimensional space. This is the example to convert from two-dimensional input space into three-dimensional input space. In practice, SVM algorithm is implemented using a kernel. In simple words, a kernel is just a function that maps the data to a higher dimension where data is separable. A kernel transforms a low-dimensional input data space into a higher dimensional space. So it converts non-linear separable problems to linear separable problems by adding more dimensional to it. There are 4 popular SPM kernels. The first one is linear. Linear kernel is used when the data is linearly separate. It means that the data can be separated using a single line. It is one of the most common kernel to be used by single line. Another kernel is polynomial for degree d-dimensional or polynomials. Poly or polynomial kernel represent the similarity of vector in the training sample in a feature space over polynomials of the original variable. The polynomial kernel looks not only at the given feature of the input sample to determine their similarity, but has combination of the input sample. For degree d polynomial, the polynomial kernel is defined as this formula. For degree d, you see here, kxi xj equal to lambda xi power t xi plus r multiplied d. So another SPM kernel is RBF or radial basis function. RBF kernel is a general purpose kernel. It is used when we have no prior knowledge about the data. The RBF kernel on 2 samples x and y is defined by the following equation here. Another SPM kernel is called sigmoid. Sigmoid kernel has its origin in neural network. We can use it as the proxy for neural network. Sigmoid kernel is given by the following equation. This is the sigmoid kernel that you have to learn it. Now it's time to learn how SPM classifiers should be implemented in Python. Until now, you have learned about the theoretical background of SPM. Now you will learn about its implementation in Python using scikit-learn. Implementation in Python is pretty straightforward. Using the SVC package from scikit-learn provides several advantages and flexibility. We have one example, classification of wine database. In order to do that, you have to import the proper library. For implementation, we use the wine database that we will describe it. The first step is import necessary library, as I mentioned here. We import pandas, numpy, matplotlib, seaborn for working with data frame and showing some figure. For using the database in scikit-learn, we import it. Yes, you have to import your database, especially the database that we are talking about. we import it, and for splitting the database into training tests, we import the related library. See, after you import it, you have to mention train and test split. For implementation SVM classification, we use SVC classification from sklearn. Finally, for scoring the performance of model, we use the metrics package and also classification report and confusion matrix from scikit-learn. For implementation purpose, we will be using a wine data set, as you can see here. It is a multi-class data set with 3 classes, 178 total samples, and 13 features are available. This data results from a chemical analysis of wine grown in the same region in Italy, but derived from 3 different cultivars. The analysis determined the quantities of 13 constituents found in each of 3 types of wine. In this section, we load data from scikit-learn library and store it into a data frame. As you can see, here is data frame. We store it in data frame using pd.dataframe. After you load the wine data, it's time to do some exploratory data analysis. Now we will explore the data to obtain information about the data. We can see the dimension of data here. Also, we can see that there are 13 variables in the data set, and the last column is the label or target for each input. Now we can see the name of features with the command. You see here, after you wrote data.head, they can show you the 5 row of the availability of data in the data frame. Let's see how many column or feature we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. 13 input feature, and the last one is target as a output feature. When you put data.column, you no need to count it like me, the previous one, I counted manually. When you put data.columns, they show you all input and output variable. When you put data bracket target.value count, they will count for you. For example, class 1, we have 71 sample. For class 0, we have 59 sample. For class 2, we have 48 sample. I mentioned to you, this wine data has 3 classes. So in order to see the percentage of sample per class, we have to use data bracket target dot value counts divided by length of data. For example, the percentage sample per class is 39.88% for class 1 and 33.14% for class 0 and 26.96% for class 2. Let's check it if the data is linearly separatable or not. This will give an initial inference to decide what type of kernel will best classify the data. For simplicity, let's plot every feature against alcohol and color the data point concerning their class. Here you see, we read the data and visualizing data points separately. You can see we already got the target based on the feature alcohol from the data column list. So it's clearly, after running the flowchart, it's clearly noticeable that the data points is linearly separated. Here you see looping through every column of data and plotting against alcohol. Means that they read all data and then target mention against alcohol. That is why you can see all the data like this. And it's clearly noticeable that the data points are linearly separatable from this side. So it's time to split data into training and test set. Training data is used to train our model, and testing is used to evaluate the trained model's performance. Ideally, 80% of the data is used for training and 20% of that for testing. But it is not mandatory. Depends on your data set and different experimental, you can change it to 70% train, 30% test, 50% train, and 50% test. It depends on the performance or accuracy that you will reach it. Here, we split the data in 80 and 20. Means that 80 training, test, 20% ratio. You know that you have to separate the target to the label, and for the rest of data you drop the target and later on you put the train data and test data, later train label, test label. Then you split it based on 80% training size, 20% test size. Now it's time to use the classification with SVM. This is the main important part that we have to talk about it. Let's build the linear SVM model using the SVC package from scikit-learn library. Function that we use here is predict. Function predict is used to predict the target Y value of feature X data. First, in order to do the classification with SVM, you have to use the training SVM model with linear kernel. Then you use the SVC with the kernel linear, random state is 10, and fit it to train and train label. Means that train data and train label. After you do it, you have to predict output for test data. In order to do that, you have to put pred equal to model.predict. I told you the function predict is used to predict the target y. So now it's time to discuss about performance metrics. In order to check the performance metrics, especially for classification and regression, you have to learn about calculate metrics. In the previous lecture, we used the accuracy parameter to evaluate the performance of our model. In this lecture, we will know about the confusion matrix and other parameters that we can use them to evaluate our model. Please read the formula and description from file. Here is the confusion matrix. What is the confusion matrix? The confusion matrix for two classes, positive, negative, or 1 and 0 is shown below. For example, if the predicted means that the positive one and actuality or actually is positive one, we call true positive, TP. And if the predicted positive is 1 and actually negative, 0, we call false positive. There are 4 quadrants in the confusion matrix, which is symbolized as below. This is we call TP, true positive. True positive means the number of instances that were positive and correctly classified as positive. We call true positive. False negative means the number of instances that were positive and incorrectly classified as negative. FP or FN. FP, false positive, the number of instances that were negative and incorrectly classified as positive. And true negative, the number of instances that were negative and correctly classified as negative. So, as I mentioned to you, we have to evaluate our algorithm or regression or classification using some performance metrics. One of the performance metrics we call precision. For precision, depends on the above confusion matrix. We have TP divided by TP plus FP. It means that for each class, it is defined as a ratio of true positive to the sum of true and false positives. Recall is another performance matrix. For each class, it is defined as a ratio of true positive to the sum of true positive and false negative. Recall equal to TP divided by TP plus Fn. F1 score. The F1 score is weighted harmonic mean of precision and recall such that the best score is 1 and the worst is 0. F1 score equal to 2 multiply precision multiply recall divided by precision plus recall. Means that you have to evaluate or calculate precision and recall, then bring it in F1 score. Support. Support is a number of actual occurrence of the class in the specific dataset. So in order to build a confusion matrix, you have to introduce one variable we call CM, for example, and CM equal to confusion matrix. The confusion matrix is the matrix that will show our performance. That is why it is important to choose the test label and predict. The next step is to defining the size of canvas. Means that you can choose the size of matrix that you want to show to us. Plot.rc params bracket figure dot fixed size, and you put by size of 8 and 6. Confusion matrix to data frame. In order to show the confusion matrix based on the data frame, you can use this line, confuse matrix equal to pd dot data frame data equal to cm, this variable that you define, and the column, and 3 column you can put predicted 0, predicted 1, and predicted 2. Means that 3 classes you want to predict, and based on 3 actual value, the real output, actual 0, actual 1, and actual 2. The next step is to plotting the confusion matrix. Many times the people, the reviewer, the examiner will see the plotting of confusion matrix, how your plotting will appear. Here you can put the heat map, and you can use the confusion matrix to show the predicted value that we got. So the next step is to print the classification report instead of showing to the matrix. It's easy to report the classification based on the numerical value. For example, the class of 0, the precision is 93%. For recall is 1, for F-score is 97%, support is 14. For class 2, for example, this value, and that value. And the accuracy show that we have F1 score and support. The F1 score is look like 94%. So in order to run the SVM with different hyperparameters, we implement SVM classifier with hyperparameters. For example, here run SVM with hyperparameters with a linear kernel and C10. What is the C10? Equal to regularization parameters. You can adjust this parameter to get more accurate result. It depends on your result. You can get more accurate result. For example, here is run SVM with RBF kernel and C10. Here is a linear kernel with C10, or with linear kernel with C10, you get this accuracy. With RBF kernel, you remember we talk about RBF kernel for SVM, and with C we call regularization parameter, you can get this value. You see this value and that value, which one is higher? You have to be careful to use which kernel function is the best for this data set. And if you use RBF kernel with, for example, C1000, you can get this value. And if you use polynomial kernel with C parameter, you can get this value. And if you use polynomial kernel with C1000, you can get this value. Different situation, I show you sigmoid kernel with C value, C parameter 10, you can get very less performance. And if you use sigmoid with the C, you can get this performance. My suggestion for you, in order to make your paper very strong, or in order to show the different experiment you can use different kernel function like this, linear, RBF, for example, the polynomial, and with different C parameters. Then finally you show different accuracy, and later on we will select the best accuracy. Once we select the best accuracy, you can find that the best accuracy came with the best linear function. This is the today's lecture that I'm trying to teach you how to use SVM or support vector machine with different kernel for Wine dataset.